oils. And it's these fats that are going to transfer from being free fatty acids to triacylglycerols back to free fatty acids when we need to degrade those. The triacylglycerols we keep in storage, or we have them moving, particularly with the triacylglycerols and the chylomicrons, and moving those into either the issue of circulation to be utilized as an energy source, or circulation to be actually moved into specific cellular structures to allow them to be stored for later use. So we're looking specifically at now the issue of fats as a potential energy source in regards to our equation of consuming fats, triacylglycerols, diacylglycerols, and free fatty acids, and how we're going to utilize those carbon backbones to give us the energy that we need. And as I said before, we need to be able to carefully carry these around with these alipoproteins because, fats are not soluble in our circulatory system. They have to be carefully carried in regards to the cholesterol and the triacylglycerol esters with these various micelle formations, which give us these chylomicrons as well as associated proteins in the surface of these chylomicrons to allow us to really do the work that is needed in the sense of transportation as well as degradation of these fatty acids as we move them to their storage area and then deposit them in their storage areas such as in the hepatocyte tissues to then actually keep them happy in regards to accessibility with other enzymes to get them to be processed to give us those short chain or long chain fatty acids. We are also recapping the issue in regards to the issue of hormones and also GCPRs playing a very specific role in this approach to activate a hormone-sensitive lipase. So this is in a situation, basically where we are wanting to mobilize the storage of our fatty acids from the lipid droplet or the hepatocyte, hepatocyte cell. And we're going to do that by utilizing a hormone system in regards to a hormone binding receptor, activating the GS system, and basically affecting the adenyl cyclase consumption of ATP to produce cyclic AMP. We already know how cyclic AMP regulates, needs four moieties to regulate the protein kinase A to then go through the phosphorylational process of this hormone-sensitive lipase that is present in the cytosol. Once that hormone is phosphorylated, it's going to be active, but also have the capacity to signal itself to move into the lipid membrane by working with other membrane proteins to cause its passage. Once that lipase is inside the lipid droplet, it's going to degrade. Remember, the phospholipases A, B, and C, lipase 1, 2, and 3, we have seen. It's going to actually work then on the triacylglycerols. And once those triacylglycerols are now free fatty acids, there's a transport system to move them out of the hepatocyte into the cytosol and then move them into the circulatory system. And with that, we're going to have a protein, in this case, serum albumin, carrying that particular protein, that particular fatty acid in circulation safely until it reaches the fatty acid transporter, which is then going to be able to pick that fatty acid off and bring it into, in this case, a myocyte, because the heart is going to use these fatty acids as a direct energy source. And it's going to go and take these fatty acids and go through beta oxidation. And then it's going to transport the products from beta oxidation into the citric acid cycle and to the respiratory chain in regards to the production of ATP, as well as giving that carbon dioxide off in the form of the Krebs cycle in the citric acid cycle. So again, we're going to look at this particular route in regards to now taking these fatty acids and degrading them to allow us to make ATP and release carbon dioxide. So again, we have this same situation in regards to the fight or flight system, where epinephrine and glucagon has that capacity to impact the adenyl activity, to increase the cyclic AMP, to go through again, not just simple dephosphorylation, but a combination of phosphorylation and dephosphorylation to regulate the emphasis, in this case, in degradation of triacylglycerols to give you the free fatty acids. And in that extent, we can then understand clearly why we need the transporter systems and the hormone regulations, as well as the various enzymes to do the job in a coordinated manner. Now, as we've talked about the issue of triacylglycerols, we can cleave off the free fatty or make the free fatty acids from the triacylglycerol, but we're then left with the glycerol backbone. So remember, this is the anchor for the triacylglycerol. So when we look at energy availability, we see 5% of our energy housed in the glycerol backbone of the triacylglycerol. 95% comes from the long fatty acid chains that will degrade a little later on. But we're going to see this glycerol specifically enter glycolysis because glycerol, with the glycerol kinase consuming ATP at an equal molar ratio, is going to produce L-glycerol-3-phosphate. And then we have a glycerol phosphate dehydrogenase system that's going to consume AD plus to make NADH at an equal molar ratio, and allow us to produce then our old friends, the dihydroxyacetone phosphate, and then have the mutase reaction to give us the glyceraldehyde 3-phosphate, which then can go directly into glycolysis. So again, we have this capacity to supplement our glycolytic pathway by adding a small amount of that material from the glycerol backbone. So again, keep that in mind in regards to when we look at the degradation of these triacylglycerols. Don't just focus on the fatty acid chains, but also think about the glycerol backbone as an energy source, also directly feeding glycolysis. So we now have these fat cells and triacylglycerols. We have glycerol in one way going through the process of glycolysis or gluconeogenesis, depending on the needs of the body, and that's happening within the liver. So again, we're going to be transporting that glycerol. If we're metabolizing the fats in a distant region, we're going to make those triacylglycerols dissociate from the lipid droplet, make them into free fatty acids and glycerol, and we're going to have the glycerol move off and take a direction, whether we're going to make it to pyruvate to bring it through to produce more acetyl-CoA to then feed the TCA cycle through the normal glycolytic route, meaning we need energy. Or if we want to store our material in form of glucose and utilize glucose as a source to provide energy in a distant organ, or utilize that glucose to produce glucagon in that particular sense, but we're really going to be not doing that because the body is going to be needing that glucose. We're not going to produce glucose through gluconeogenesis to produce our storage material in the form of glycogen. So we're going to basically utilize that glucose mostly to feed ourselves. But the fatty acids themselves, and they can be varied lengths of chains and saturation, are going to go through fatty acid oxidation in other tissues. And they're basically going to feed the production of acetyl-CoA. So they're going to bypass the pyruvate dehydrogenase complex, and we're going to move that acetyl-CoA directly into the TCA cycle to give us carbon dioxide and water as we go through the oxidative phosphorylation system. But again, we need to consider two systems. We need to consider the fatty acid activation coming from the fatty acid lipid storage area, as well as the fatty acid transportation. And we're going to do this importantly by moving the fatty acids into the mitochondria, because this is where the TCA cycle is. And we're going to basically have to have some controlling system to allow us to go through a process to modify the fatty acids, to bring them into the mitochondria. So we can regulate and control what fatty acids are getting into the mitochondria. We're going to do that through the esterification of the fatty acid chain to CoASH enzyme or CoA. We're going to then go through a process of displacement of that CoA, which is a great leaving group, is going to go through the trans esterification to the carotene. Now, with the carotene, we are then going to then have that capacity to move that molecule across the membrane of the mitochondria. And the mitochondria is a very special membrane. We'll have a look at that in a second. And you need to understand this because it's going to have implications when we look at ATP production. And I'll show you in coming lectures why. And then what we're going to actually see is the carotene come back to the coenzyme form, because what we're actually doing is basically having the capacity to move the fatty acid and regenerate, importantly, or consume CoASH in the mitochondrial membrane. So let's have a look at what I'm talking about here in regards to this esterificational step, trans-esterification to carotene, and the movement back to coenzyme esterification, given that this is an important approach in the process of moving fatty acids into the mitochondria. So let's first look at the fatty acid activation. So here we have a system where we're going to be looking specifically at a non-R group. So we have a fatty acid, and you have many long chain carbon alkyl chains, double bonded and single bonded. But it's the carboxylic acid that we're very, very interested in. It's going to go through an esterification process utilizing ATP, but this time attacking the alpha bond in the ATP and producing, again, that pyrophosphate molecule, which can be then further broken down to individual inorganic phosphates. So let's have a tack in regards to the fatty acid acyl coenzyme synthase, which is going to utilize that ATP and the fatty acid to give you this fatty acid acyl adenylate form in regards to a single phosphate group and adenosine attached to the fatty acid carboxylic acid. Now, this particular guy in its form is going to give us AMP, and this provides a great leaving group for us to actually now attach the coenzyme A to that particular carbon position, giving us the fatty acid acyl coenzyme constituent, so CoA there. Now, to drive this reaction, we need to basically utilize this guy also, the pyrophosphate that's originally come from the ATP, and degrade it then between the beta and the gamma bond to give us the two inorganic phosphates, which is going to give us ideally 19 kilojoules per mole in the negative, so it's very favorable. For the two-step process, in us allowing us to actually go through esterification, utilizing ATP and the fatty acid to make the fatty acid acyl adenyl form, and then to give us the free fatty acid acyl CoA, that is negative 15 kilojoules per mole. So if we look at the whole process of reversibility, fatty acid plus CoA and ATP is going to give us the fatty acid acyl CoA, AMP, and two moieties of inorganic phosphate at negative 34 kilojoules per mole. So that's actually pretty good. But again, this is seen as a priming reaction. Okay, so it's a priming reaction to give us this constituent, which is then going to be utilized in the transport system. So let's have a look at the next stage. So the transport system, as I said, the mitochondria, the powerhouse of the cell, as you've known from your biology, is actually very interesting. It actually has two membranes and an inner membrane space. And this inner membrane space is really important, and we'll come back to this at a little later. So we have an outer mitochondrial membrane and an inner mitochondrial membrane. And so we're going to have the capacity to move the fatty acids into this system and allow its transportation into the mitochondrial matrix. And so what we're actually going to do is inside the mitochondria, we're going to present it with the esterified trans fatty acid, or esterified fatty acid, and we're going to displace the coenzyme component on the thiol ester, and we're going to utilize carotene, and I'll show you the structure of carotene in a second, in regards to utilizing this as a displacement reaction to give us a carotene ester of the fatty acid. Now, with that carotene present, there is a very specific and selective transport system to move that through, and that's the carotene acyl transferase number 1. With that in mind, what it does, it has the carotene attached to it, and has then the capacity to move into the inner membrane space. With that assignment, it still can't get through the inner mitochondrial membrane unless it's going through the transport system. And in this case, the transport system will only recognize the carotene fatty acid form. In this case, we bring it through the inner mitochondrial membrane space and give us then the fatty acid carotene ester. But this is no good to us inside the mitochondria. It has to be regenerated back to the coenzyme constituent. So we're going to consume CoASH and basically displace the carotene like we displace the CoASH on this side, and regenerate the coenzyme A fatty acid, and basically have the carotene move through the transport system. Remember, this is a co-transport system, so the carotene is coming through, the carotene fatty acids going the other direction. So we're getting this co-transport component coming in through the carotene acyl transferase number 2 to do its job, and then replenish the carotene supplies in the cytosol to then repeat the whole reaction again. So we're going to have a movement of the carotene coming out and the carotene fatty acid coming into the mitochondrial membrane matrix, and the regeneration of the fatty acid acyl-CoA to be the starting product in regards to the degradation of our fatty acids, or our R group here, by utilizing this coenzyme component. So again, it's an illustration of the esterification of carotene via the Thaler ester displacement reaction, transporting specifically through a co-transporting system, and allowing it to get into the mitochondrial matrix of the system. This is where all the good enzymes are, and then retrans-esterifying that back to the coenzyme component through, again, the formation of the Thaler ester linkage. So that becomes then the great component of starting the degradation of the R chain in regards to the fatty acids. So hopefully that transport system is clear in your mind, and it illustrates a couple of systems in regards to moving through 2 membranes, having a recognitional transport system in regards to derivatizing and utilizing that coenzyme A as a good leaving group, and regenerating the coenzyme constituent by consuming CoASH in the mitochondrial matrix side. So here we have the carotene molecule here. It's pretty small in regards to the recognitional components of the transport enzymes, the acyl transferases. But importantly, once it is actually attached to the fatty acid, it's actually then committing that fatty acid to be transported into the mitochondria, which will then undergo beta oxidation. So again, it's really important to have this system. And this is where we see a lot of interest in obesity, because people recognize if you can't metabolize fatty acids, these fats are going to be stored elsewhere. But if you can promote their particular metabolism in the mitochondria, you'll get a lot of energy, but also you'll be able to keep the fat stores in a manageable state. So people are looking at how to utilize this particular system to increase metabolic array of activities in the mitochondria. So again, we have the molecule of the coenzyme A, and here's the active Thaler ester group, and we're basically going through the displacement of this hydroxyl group onto that coenzyme constituent in regards to producing a displacement of Thaler ester reactive group. So once we've got that commitment in regards to the fatty acid CoA component, we're moving it into the mitochondria to go through beta oxidation. So the interesting component here is the fate of the acetyl-CoA in regards to the production is really dependent now on its transportation and where it's actually being made. So let's think about this mitochondrial membrane situation. We can get acetyl-CoA on the cytosolic side in the cell by going through and degrading glucose and pyruvate, pyruvate dehydrogenase. We can do this by amino acids. And we're going to come back to this oxalate, malate, and citrate shuttle in a second. Oh, citrate. Remember, citrate is part of the TCA cycle. So we have, and same with oxaloacetate, we've studied this little part before in regards to the phosphoenolpyruvate to produce malate, and even then taking the oxaloacetate to then actually do the reverse to produce glucose. Remember that? But again, this time we're now looking at, importantly, how we need to also move now citrate in to the system to allow us to regenerate acetyl-CoA and go through fatty acid synthesis. So again, here we're now having biosynthesis, not degradation, but biosynthesis of fatty acids that are occurring in the mitochondria. And they are really essential with this citrate transporter. So again, in the coenzyme is in the matrix, in the cytosol component, where we're going to see CoAsh being actually produced in the form of the acetyl-CoA coming from glucose amino acids. We'll come back to that in this week or next week, I think, and going through pyruvate to produce that acetyl-CoA, and then using that acetyl-CoA with the oxaloacetate, the same system we had within the TCA cycle with the citrate synthase, and now producing citrate. Now that citrate is not going to go any further really until we actually move it into the mitochondria. And within the mitochondria, we're going to then be able to, so I got that the wrong way around. So this is the matrix side, my mistake. This is the matrix side of the mitochondria here, the matrix side of the mitochondria, the cytosol of the cell. Okay. So in this case, we have all our acetyl-CoA forming through the citrate synthase, and this is all within the mitochondrial matrix, and then moving this citrate out into the cytosol. So we can have our TCA cycle quite happily going in the mitochondrial matrix, doing its job, degrading the citrate, going through the isocitrate, the alpha-ketoglutarate, etc., making that FADH and NADH2 and GTP. But we can also then take, if need be, and we want it in a happy cell process where we have abundance of energy, we really don't need the TCA cycle making all the NADH and FADH2, but we can then move that citrate out to become then a process for fatty acid production in the cytosol, because fatty acid production does not occur within the matrix of the mitochondria. Now, in this case, what it also illustrates importantly is how to move reducing equivalents in a mock form through citrate from one side of the mitochondrial membrane to the other, to the cytosolic side. And this is really important because the cytosol, kind of has a deficiency in regards to meeting its needs with NADH as well as FADH2. So what it actually does is has the capacity to utilize the NADH electron carriers and the form of ATP to allow us to regenerate the acetyl-CoA on the cytosolic side of the cell. So the acetyl-CoA is not completely only restricted within the mitochondrial matrix given the TCA cycle, but this is an illustration of how we're basically going through the degradation of fatty acid, pyruvates, and amino acids to give us this citrate, which can move through a transporter, through the citrate transporter, to the outside of the cytosol. Once that citrate is there, through the citrate lysase, we have the capacity to consume coenzyme A, consume ATP, and regenerate acetyl-CoA as well as oxaloacetate. And this oxaloacetate can also consume NADH and make malate, which can then produce phosphoenolpyruvate if we desire, or even oxaloacetate can produce phosphoenolpyruvate if we desire energy in the form of glucose. But we're not going to be doing that because really, if you think we're doing fatty acid synthesis, we're going to be in a happy state cell. We are not going to be able to really utilize that glucose that we have. We might want to put that glucose into storage, or we're going to put this stuff elsewhere. And we'll see this particular citrate shuttle come back to us a little later on. This is all I want to show you at this stage, is moving the acetyl-CoA from the matrix of the mitochondria to the cytosol of the cell. And we do that specifically for fatty acid synthesis. And again, this is an approach that people are trying to look at in regards to the citrate synthase, lysase and citrate synthase and citrate transporter as a key way to regulate the production of fatty acids, i.e. what we see in some people of obesity. So the fate of acetyl-CoA is really based now on this transportation system in regards to disguising it as a form of a molecule which has an appropriate transporter to allow it to move through, but also matching it with particular enzymes to give it the capacity to regenerate that acetyl-CoA, but also, again, account for the byproducts, in this case, oxaloacetate, and the utilization of that oxaloacetate in further metabolic systems within the cytosol. So again, compartmentalization, sequestration, transportation, and matching it with particular enzyme systems, either side of a membrane system that might be unique and have its own regulatory components, are going to provide us the capacity to favor one system over the other, depending on the needs of the cell, whether it's a happy cell or an unhappy cell in regards to its energy systems. In this case, this would illustrate a system that is basically very happy in regards to synthesis of fatty acids are only going to occur when all the energy requirements of the cell are being met, and there is a surplus amount of energy that is housed or being produced within the mitochondria and can be then utilized for fatty acid synthesis. So again, it's an illustration of masking, transportation, matching it with enzyme systems to get what ideally you want in regards to making a happy cell. So let's have a think about the process of beta oxidation. And this is now contending with the fatty acid alpha chain that we have now derived from our triacylglycerol using the various phospholipases. And what we're going to do, we're going to focus specifically on this carbon chain. So there's 1, 2, 3, 4, 5, 6, 7, 8, 9, 10, 11, 12, 13, 14, 15, 16. So this is a C16 semicolon 0. There is no double bond. So this is a saturated fatty acid. And it's going to go through a number of steps of beta oxidation. And I'll talk about these in a second. But I want to give you the big picture, because each beta oxidational process is going to cleave from the carboxylic acid end 2 carbons at a time. Bang, bang, bang. A very repetitive reaction. You're going to have to know this reaction and be able to draw it and move it through. It will be on exam number 3 and maybe on the final. In this case, what we'll see is the generation of 1, 2, 3, 4, 5, 6, 7, 8 acetyl-CoA moieties, because remember, acetyl-CoA is 2 carbons in length. So basically, we're cutting off 2 carbons at a time of an equal number of a saturated fatty acid to give us 8 moieties of acetyl-CoA. Now, the 8 moieties of acetyl-CoA is going to provide us 16 moieties of carbon dioxide. In that process, with that carbon dioxide, we're going to get the FADH2, and the NADH is going to produce us an equivalent of 64 electron equivalents. They're going to be sunk into the FADH2 and NADH, and they are then going to go into the respiratory chain, or the electron transfer chain, as we will study a little later on. With those transfer of electrons, we're going to see the electrons being deposited with utilizing molecular water and hydrogen to produce metabolic water, and in the same process providing a proton gradient to allow us to take ADP and inorganic phosphate to make our energy currency in ATP. So this is the bigger picture. But what we're focusing on today is stage 1 and feeding of stage 2 in the form of acetyl-CoA. So when we look at fatty acid oxidation, which is illustrated on page 655, it occurs specifically in the mitochondria, not in the cytosol, only in the mitochondria and in another specialized organelle called the peroxisomes, which we studied a little bit about that in regards to the production of hydrogen peroxide in the form of the stress factors. And we're going to talk more about this a little bit more when we look at dysfunction in relation to the respiratory chain. So in this case, we have 3 forms of oxidation for fatty acids. We have a beta, an alpha, and an omega. And I want you really only to focus really on the beta oxidation. We'll talk a little bit about the alpha and omega, but beta is the one that usually comes up on the exam. So beta oxidation is the successive removal of 2 carbon units in the form of acetyl-CoA from the disintegrating or truncational chain of fatty acids. Now, with every removal of 4 hydrogens or 4 protons, we get with each acetyl-CoA. So again, that's going to give us that capacity to get those individual electrons out of that system and have a high flow through of electrons in the TCA cycle, the Krebs cycle. So there's 4 basic steps that we're going to have to know for beta oxidation. So this is a hydrogenation reaction, a hydration of a double bond, oxidation to a ketone, and a thiolytic cleavage by coenzyme A, which is actually going to be the repriming of this particular system in regards to giving you the carboxylic acid end with the CoAsh component to then go through the whole system again and take another 2 carbon moieties off to give you a shorter and truncated fatty acid. So let's have a look at these 4 basic steps in regards to the repetition of the system. So there's 4 basic steps in the production of acetyl-CoA, and I illustrated up here, and it's 2 in the book, in regards to this carbon 16 moiety, so it says carbon 14, but it's actually carbon 16 if you think about it, in regards to this is the first one that's going to come off, and it's going to give us 1, 2, 3, 4, 5, 6. So 1, 2, 3, 4, 5, 6, 7 moieties of a fatty acid. Okay, and then we're going to be left, interestingly, at the last cleavage point, 2 moieties of acetyl-CoA, because the last constituent is going to be 4 carbons in length, and we're going to cut that in half and give 1 acetyl-CoA and 2 acetyl-CoA. So this is why we only see 1, 2, 3, 4, 5, 6, 7, because the last one is going to give us 2, not 1. So let's have a look. So here we have our C16. Here's our alpha and beta position. We have to recognize those. This is also palmitol CoA with the CoAsh present. So we've actually done the priming reaction. We've got it moved into the mitochondria, gone through the the carotene shuttle, moved it through the double membrane, and regenerated the coenzyme fatty acid on the mitochondrial matrix side of the mitochondrial membrane. So we're going to consume FAD to make FADH2. So we're already supplementing our electron pool in the form of being able to make energy in the process of degradation. So again, ultimately, that's going to give us ATP. So what we see here is this carboxylic acid as a key position with this alpha carbon, and allowing now a change in a bond situation between the alpha beta carbon, and this will produce a double bond and allow us then to have that 1 hydrogen being positioned. So with this particular one, with the enol coenzyme A hydrase, we're going to use in molecular water to supplement this and attack this particular position and basically break the double bond and give us an alcohol. And with this as alcohol component, it gives us then the start in regards to the whole degradational process. So we're going from an alkyl chain to an alcohol, and then to basically a ketone. So again, let's have a look what's going on in regards to the next step. So we've now got the alcohol being present in the form of, this case is the hydroxyl acyl-CoA, and we're going to again produce NADH by consuming NAD plus through the hydroxyl acyl-CoA dehydrogenase. And that NADH is also going to ultimately allow us to produce more ATP, because that's going to go into the respiratory chain. So we're doing all this preparation in regards to the degradational situation, which is going to be number 4, when we see basically the ketone form, or the ester form in this part, now actually having this capacity to recognize this guy here. So here's our 2 carbon constituent, and CoAsh coming in through the thiolase to actually attack this bond here and cause a cleavage there. With that cleavage, we produce then the acetyl-CoA, and then the degraded fatty acid, not losing 2 carbon constituents, so no longer carbon 16, but carbon 14, but already primed, ready for the next reaction. So again, all the way back up to number 1 and bring it through again, producing FADH2, producing NADH, going through this same process again, utilizing the alpha-beta, so you've got to be able to recognize where the alpha-beta bonds are in regards to that double bond formation, the hydrogenation of the double bond to give you the alcohol, then the ketone, and then the thiolysis, the cleavage, in regards to the generation of the acetyl-CoA. So again, dehydration, hydration, oxidation of a ketone, thiolytic cleavage. So again, time and time again, the 4 steps that we'll do. So you're going to repeat this time and time again in regards to the production of acetyl-CoA and a shortened chain of the free fatty acid. And again, this is saturated. So let's see what happens when we do double bonds. We'll see that a little bit today. But again, I could put a radio label in a position somewhere, maybe distant in regards to the fatty acid chain, and ask you how many times would you have to undertake beta oxidation to get the acetyl-CoA that is going to have the radioactive form, and where is the radioactive form going to be in the 2 carbons. So again, you're going to have a very careful instinct in regards to how this chemistry is done in regards to the positioning of the radioactive carbon or hydrogen or oxygen that might be present in this particular molecule. So again, that pops up on the 3rd exam. And you'll have some practice in this in the homework as well as in the recitations. So 4 basic steps for the production of acetyl-CoA. So what happens though when we have a saturated fatty acid? So the illustration we provided you there was unsaturated, just simple single bonds. But if you think about already the structure of a saturated fatty acid, it actually already provides us the capacity to have the double bond already present between the alpha and beta carbon. And that basically gives us the capacity to jump a few steps. So if we go back here, this is mimicking what we see in a saturated fatty acid, a double bond. But we've got to make sure we have the right carbon constituents in regards to the numbers. Remember, those bonds are usually from the 9 to the 10, the 10 to the 11, the 11 to 12, and 13, and 14, 14, and 15. So again, there has to be some correlation to the capacity to deal with this particular constituent and have the right number of carbons to get to this double bond. But let's have a look at the situation here. So the oxidation of fatty acid in a saturated form is basically taking the system, what we've previously come familiar with, and looking at this particular guy here. So this is mimicking a saturated fatty acid bond saturated fatty acid bond in the fatty acid. So we're going to have to be able to then deal with this, but I want to also tell you something a little bit about the nomenclature. So we have very long carbon fatty acid chains, medium length and short length. So these are the different carbon lengths that we are going to actually utilize. Now, some of these particular long fatty acid chains, before they get into the transport system, need to be actually degraded, because the carotene shuttle, or the transport system that uses carotene to move the fatty acid into the mitochondria, is restricted by the length of the carbon chain. So there might be some thiolysis activity that already needs to be done in the cytosol to deal with some of these fatty acids to cut them up into a manageable size. So we're going to have a little bit look. Usually carbons from no larger than 14 carbons in length are usually the ones that are being transported into the mitochondria. So let's have a look at what's going to occur with that saturated double bond. So here we have our same situation in regards to this particular step, allowing us to take that double bond, that saturated double bond in our saturated fatty acid chain, and go through the enol-CoA hydrase with water and allow us basically to produce that hydroxyl constituent in regards to what we previously saw. And then it goes through the normal oxidational process in regards to allowing us to cause the thiolysis cleavage in regards to having that hydroxyl position, now sinking those electrons and those protons to give you that double bond in this position to form the ketone, and allowing us then to take the NADH to make more energy, which is we will fully understand later on. This time we now produce the two ketone components, and as you can see, the symmetry in regards to this guy is going to have the flanking bond, which is going to be susceptible to nucleophilic attack, and allow us basically to cleave this position, bringing the coenzyme in here and allowing this to form a new CoAsh component, and then this become protonated, and then we form our first form of acetyl-CoA, dealing with that double bond saturation. So again, it's less stable, cleave it, and then we'll continue it again in regards to forming acetyl-CoA, and now the remaining constituent. But note importantly, we have to reassign then the alpha and beta carbons. So again, every time we do a cleavage and we remove two carbon constituent from the acetyl-CoA, in the form of acetyl-CoA from the fatty acid degradational chain, we are going to have to reassign the alpha and beta carbons so we can identify the reaction that we need to do again. Now, the reason the thiolysis works so well is this carbocation resonance structure with the ketone component. And this particular proton becomes slightly acidic and therefore becomes a great leaving group if presented with coenzyme A with those electrons to attack this carbocation component on the ketone component. And again, allowing us to reestablish the coenzyme constituent on that new carbon or that new double bond oxygen, and again identify this as now another alpha position, and this is the beta position, because again, this is where the next cleavage is going to take place in regards to the further degradation of this long chain fatty acid to bring it down to carbon 12. So again, this repetitive process occurs of those 4 steps time and time again. So we get through the whole process, and we should be able to clearly understand the overall nomenclature in the balance reaction that we see in this particular system. So we have, as I said, it's a carbon, let's just do the saturated version, unsaturated version, where we're going to see, well, it doesn't really matter if we do the saturated or unsaturated, we're still going to end up with the same products in regards to the number of acetyl-CoAs. But we're not, if it's unsaturated, remember we're going to be missing a couple of steps in the first part if we're going to account for the NADH and the FADH2. So again, there's a little bit of a difference in regards to the both systems. So here we have our 16 carbons. So we're going to go through cycle 1 and produce 1 carbon, 2 carbon constituent, second, a third, a fourth, a fifth, a sixth, a seventh, and then finally, when we come to our 4 carbon constituent, we're going to be producing the cleavage of 2 4 carbon constituents to allow us to produce two carbon constituents, which is going to be then the acetyl-CoA. So we should be able to think about the full reaction in regards to if we go back and do all the individual counting in regards to the number of FADH2s, their consumption, the number of NAD pluses being consumed, and the production of NADH plus protons, the number of CoAsh enzymes being consumed in regards to the whole nomenclature of the system, where we'll see palmitol, which is unsaturated carbon 16 semicolon 0. Palmitol CoA is going to give us 7 CoAs, or consume 7 CoAs, consume 7 FADs, consume 7 NADHs, and 7 molecular waters. Because the final stage, as I said, is a carbon 4 constituent, and it's going to break that to produce the 2 carbon constituents. So it doesn't have to go through the full cycle that we've previously seen. And that is ultimately going to give us 8 acetyl-CoAs, 7 FADH2s, 7 NADHs, and 7 protons. So we should be able to write an equation in regards to the balancing of this particular reaction with saturated and unsaturated fatty acids. So again, this is something to be considerate of. And always remember the last step in this case with an even number fatty acid is always going to give us 4 carbon bases at the last cycle, which will go through thiolysis and produce 2 carbon constituents of 2 carbons each, which is in the form of 2 moieties of acetyl-CoA. That's a real key component and point to think about. So when we look at the overall net energy gain from these individual reactions in regards to the various enzymes and then putting those acetyl-CoA into the TCA cycle. So here we've got this reaction here, we're producing 8 acetyl-CoAs. We've already got some great energy carriers that are going to give us some more energy in regards to going to the oxidative phosphorylation cycle. So let's now account for what's going to happen with those acetyl-CoAs. Those acetyl-CoAs, we're going to be able to produce a lot of energy in regards to going through the isocitrate dehydrogenase, and as well as the alpha-ketoglutarate dehydrogenase. Succinyl synthase is going to give us nothing, but it's going to give us ideally 8 moieties of GTP. We're going to see succinate dehydrogenase producing more FADH2 and NADH. So you can see the amount of equivalents we're going to see in the form of ATP. Now, I see here where someone's going to say, oh, well, you've got 108 here, Dr. Bingham, but why do you have 6 here? Remember we talked about that issue regarding the plus or minus 2 ATP equivalents for oxidation of a molecule, and that is dependent on that initial coupling, that coenzyme A coupling, which requires 2 moieties of ATP to actually do that, to put the fatty acid, the palmitoyl, to make it the coenzyme A. So that's where we get that differentiation between 32 or 30 ATP moieties. So as we add everything up in regards to the FADH2s that are being formed and the NADHs as well as the GTPs, which are equal to ATPs, we start seeing that there's a fair amount of energy coming from these fatty acids. So here we have the full oxidation of a unsaturated fatty acid, single bond. We're going to consume 32 moieties of oxygen, 108 moieties of inorganic phosphate, and 108 moieties of ADP. We're going to get coenzyme A being released, because this is what's coming off here. We're going to have 108 ATPs formed, 16 carbon dioxide, and 32 moieties of water. So we have a net gain of 106 ATP. So that's a fair amount of energy we're getting from a single fat. And that's why we use fats as an energy source, as an energy storage unit, because they are highly accessible. They have an enormous amount of potential in storing energy, and we can harvest that energy from those particular systems. And again, we've got to remember what the equivalents are to the forming of the ATP equivalents from the electron carriers. In this case, 1 FADH2 equals approximately 1.5 ATPs, 1 NADH equals roughly 2.5. So the NADH are the good ones. They're going to carry a lot more energy equivalents to that of the FADH2s. So again, keep in mind when we see their degradation, in this case of a 16 carbon fatty acid, what ultimately you're actually going to be gaining when you fully oxidize that to metabolic water, carbon dioxide, and the form of ATP energy carrying through the integration of the beta oxidation now into the TCA cycle and later into the oxidative phosphorylational system and the electron transport system and respiratory chain to give us that ATP. So again, this is the bigger picture, and we're going to have to be able to kind of think about, importantly, and study the beta oxidational system and account for the numbers of FADH2 and NADH being produced in this system. Okay. Now, what happens when we have some other odd amino acids, odd fatty acids? So here we have an oxidation of a mono unsaturated fatty acid. So we've already discussed the easier system when basically it is a fatty acid with that particular double bond going through the jump start in regards to what we've seen normally with the saturated double bonds. We see that double bond formation requirement, but this time we're going to have to deal with a double bond present in a monosaturated fatty acid. So in this case, this is a C18 1 delta 9 fatty acid. So it has the double bond in the delta 9 position. So this is why we got you to learn that particular nomenclature. So what we're going to first do, we're going to have some auxiliary enzymes playing a role in regards to mimicking something which we are more suitable in regards to the normal beta oxidational process, which is to do with the saturated form. So here we have our C18 1 delta 9 being presented, but we can go through steps 1, 2, and 3 of beta oxidation first off without contending or dealing with that double bond. So we can go through one step and remove 2 carbons, go through the second step and remove 2 carbons, go through the third step and remove 2 carbons in the form of 3 moieties of acetyl-CoA. We will stop at the third component because this is what we're now dealing with in regards to this double bond constituency in regards to a 12 carbon constituent. So this would be illustrated as C12 1 delta 1, 2, 3. So again, we change the naming nomenclature. So this is delta 1, 2, 3. Okay, so it's a C12 semicolon 1 delta 3. Okay, because the delta 3 has a specific enzyme that allows this double bond to be transferred from the 1, 2, 3, 4. So this is the 3, 4. It moves that double bond to become the 3, 2 double bond. Now, with that 3, 2 double bond, that's exactly like we saw in the previous situation with the unsaturated, with the saturated fatty acid degradation. So let's go do the enzyme work using the isomerase and allow us to basically produce now that 2, 3 double bond, which is now illustrated here. And that is identical to one of the steps we have normally in the beta oxidation for the saturated fatty acids. So again, have a look here. I want you to focus on here. 1, 2, 3. So we have the double bond at the 2, 3 constituent. So let's go all the way back. Okay, here. Yes, so here. So in our first step of dehydrogenation, we have 1, 2, 3. So we have our 2, 3 carbon double bond here between the alpha beta carbon, which is in the normal process of the hydration and then the formation of the hydroxyl, then the dehydration to form the ketone, and then the thiolysis between the alpha and beta in this position to give us the generation of the new thiol ester and the cleavage of the 2 carbon constituents from the carbon number 1 position. So again, it's this continual repetitional situation as occurring. We're modifying our fatty acid to fit the enzyme system that we presently know as the form of beta oxidation. So again, this is an issue of an oxidation of a monounsaturated fatty acid. So that's pretty easy to contend with in regards to having a similar intermediate. And once we've got rid of that double bond, we can then go through and treat this as a saturated fatty acid because there's no other double bonds being present. So in this case, we would actually go through 5 cycles of beta oxidation. And remember, the 5th cycle will produce a carbon 4, which will go through the thiolysis cleavage to produce 2 moieties of acetyl-CoA. So it doesn't have to go through the whole step. So it's only 5 steps of beta oxidation, and which will give you the final 2 steps. Will give you 2 moieties. Will give you then the full 6 moieties of acetyl-CoA. So again, that's a pretty illustrated situation of beta oxidation in the monounsaturated fatty acid. First, we're going to do some normal fatty acid degradation, get that carbon double bond in the position of number 1, 3, and 4, do the isomerase, bring it to 3 and 2, and once we've got that 3 and 2, we can then treat it as a normal beta oxidational process that we've seen previously. So there's these conserved reactions in life chemistry, in biochemistry. So let's have a look where we see a double bond being produced in regards to sinking electrons and protons in. So we're taking protons from these guys here and forming a double bond. We're then hydrating it, utilizing water to give us the hydroxyl form and the destruction of that double bond. And then we're changing that double bond, that single bond hydroxyl, to form a double bond, taking the protons and the electrons and sinking it into NADH to give us that ketone component. So that's in beta oxidation. But we've already also seen this in regards to the citric acid system, in regards to our friend oxaloacetate and moving it through in regards to succinate. So again, let's have a look. Double bond not being present, but then with the sinking of those electrons into FADH2 as well as the protons, giving us that formation of double bond. We also then have the rehydration of that particular system to give us then the hydroxyl form. The hydroxyl form can then be then further reduced, sinking those double bonds, sinking the electrons and the protons into NADH to give us that double bond constituent in the form of a ketone. And the same thing with amino acids. We'll talk about these amino acids later on, because we're going to look at the oxidation of these amino acids, because hello, they give us something very similar, which we can utilize potentially as a source for energy. And we'll talk about those when we look at the degradation of amino acids. So the illustration I'm trying to put here is there is conserved reactions in chemistry, in biochemistry in particular, that nature has utilized because they're energy efficient, and you use the same electron transport systems to sink those protons and electrons in the system to give us a safe capacity to move those materials through to allow us to produce electron equivalents. Now, what happens when we get a little more complex in regard to now a polyunsaturated fatty acid? So this has two bonds. So this is a C18 semicolon 2 delta 12 9. So again, we have two double bonds to contend with. So, but in the same process that we saw previously, we can use the same enzyme, the isomerase, to first deal with the first double bond in this position, the 9 and 10 position. But first off, let's go through 3 cycles of beta oxidation to get it to that carbons 1, 2, 3, and 4. Okay? So again, we're going to do the same system that we saw before. In this case, we're going to use the isomerase to move the double bond from 3 to 4 to 3 to 2. Again, allowing us to identify the alpha and beta carbons. In that particular process, we now have this commodity, which we can potentially deal with in regards to the normal process of beta oxidation to give us the 1, 2 carbon constituents in regards to having us go through the hydroxylational form. So let's have a look what's going to go on. So we've gone through 3 cycles of beta oxidation, giving us 3 moieties of acetyl-CoA. We've established where the alpha and beta bonds are, the alpha and beta carbons are in relation to their numbers. We're going to use the enol coenzyme isomerase at the 3 delta 3 delta 2 position, and then cause that double bond to be positioned here between the 2 and the 3 carbon, meaning the alpha carbon and the beta carbon. We're then going to go through another process to allow us to deal with this guy, because now this is in the option to allow us to go through a reductase to give us acetyl-CoA. So again, we get one particular cycle coming off, thank you very much, and allowing us now to contend with a situation of now moving this double bond now back to the 3 to the 4, 5 was to the 4, 5 position really, but we've taken this guy off in the form of 2 carbons, and we're basically left with this constituency here, where again we have to re-identify the carbons 1, 2, 3, 4 and the alpha beta bonds, and in this time we're going to be using a reductase consuming NADPH to get rid of this double bond, sink those electrons in there, and then move that particular constituency in regards to this double bond becoming in a 3, 4 position. So this guy is going to go through the reductase process and then move this double bond into this position into the 3, 4. With the moving on the 3, 4, we then have the capacity then to just go through again beta oxidation. We can identify the individual carbon constituents of the alpha and beta carbon, and this is where we're going to do the cleavage, and we're going to then produce a 2-moiety acetyl-CoA with a new CoAsh component. So let's see what goes on in that next step. So again, we're moving the double bond, we're producing acetyl-CoA using the reductase. The reductase is then going to allow us to reduce these 2 bonds to give us the 3, 4 double bond constituency, and then allow us to then promote this system. So with that promotion, we're going to see then this guy, here we go, the trans delta 3 in that position using the normal isomerase to give us then the movement of that double bond like we saw previously back to the 3,2 position, and then allowing us to actually go through the hydration reaction and break that double bond and allow us to form acetyl-CoA. And then once we've contended with that, we now have a new acetyl-CoA constituency at position number 3. And now we have a saturated alkyl chain, which we can then do the normal beta oxidation cycles, 4 cycles, to produce 5 acetyl-CoA constituencies. So again, we have the capacity to be able to handle these di-unsaturated, mono-unsaturated fatty acids and fatty acids of an equal, even chain length. So again, we keep modifying our system, our fatty acid substrate to conform with the enzyme systems that we have in this main path of beta oxidation. Now, what happens when we have odd fatty acids? So think about this. We have a carbon 16 moiety. It's going to go through 7 cycles of fatty acid oxidation. The final fatty acid oxidation is going to give us a 4-carbon constituent. That 4-carbon constituent can go through a thiolysis reaction to give us 2 2-carbon constituents. So when we think about fatty acids of an odd number, we're going to do everything we do similar and the same until we do the last cycle. So in our last cycle, we're going to have a problem where we're going to see a 5-carbon constituent, not a 4-carbon constituent, because normally, as I said, with a 4-carbon constituent, we're going to break those down to produce 2 acetyl-CoA moieties. In this case, when we're looking at odd number fatty acids, the last cycle is going to give us that 5-carbon constituent. And what we're going to have is a problem with a 3-carbon constituent product. So we're going to take the 5-carbon constituent, still going to be able to take off 1 acetyl-CoA moiety, but we're going to be left with a 3-carbon constituent. And that 3-carbon constituent is a friend that we know, propanol-CoA. Now, propanol-CoA is actually going to be modified through a number of enzymatic steps to produce a friend of ours that we know through the TCA cycle as succinyl-CoA. So again, this gives us the capacity to produce an intermediate that now feeds the TCA cycle from odd number fatty acid degradation. So let's have a look. Most of these odd fatty acids are mainly found in plants and in marine organisms. And they use this propionate as a potential source of carbohydrate formation through succinyl-CoA, feeding oxaloacetate, feeding the phosphoroenol pyruvate to then make glucose. Now, in some cases, fermentation of carbohydrates by rumen organisms such as cows have this capacity to utilize this system. We don't, because we don't have those types of enzymes. But also, we utilize these in regards to propanol-CoA being utilized by yeast in regards to making bread. So again, propanol-CoA is a carbon source, like we saw with acetate as a carbon source to different organisms, and they can utilize those carbon sources as a source of energy. So in the normal process of beta oxidation, we're going to handle the odd number fatty acid system, whether it be saturated or unsaturated, monosaturated, mono-unsaturated or di-unsaturated, whatever. We're going to handle it the same process until we get to that last stage of degradation, where we're going to be left with a 3-carbon constituent. The 3-carbon constituent is going to go through and be formed this constituency in regards to propanol-CoA. Propanol-CoA is going to go through the carboxylase enzyme, very similar to what we saw previously with the formation of oxaloacetate, utilizing the biotin dependent system using bicarbonate. We've seen this before, and this time producing methyl-manyl-CoA. Methyl-manyl-CoA is going to go through an imperization in regards to producing N-methyl, L-methyl-manyl-CoA from D-methyl-manyl-CoA, and with the methyl-manyl-CoA mutase reaction, which is an enzyme-dependent cofactor, so there's coenzyme B12, we will then produce succinyl-CoA. So again, there's a couple of steps. There's a carboxylation regarding using biotin, an imperization, and a rearrangement to produce the succinyl-CoA. So we now have a clear understanding how to deal with saturated fatty acids which are odd number. We know how to deal with unsaturated fatty acids at an even number, unsaturated fatty acids as an odd number, unsaturated fatty acids in a single fatty saturation position, or fatty acids in a double saturational position. So we have now a whole combination of capacity of dealing with a lot of different fats in regards to allowing these moieties to enter beta oxidation. And again, some of these do pop up on the exam. So when we come to our final thing in regards to understanding what we need to look at, we've got to think about the revising and naming of our fatty acids. We've got to know the system. We've got to be able to identify the carbons 1, 2, 3, and 4. We've got to be able to identify the alpha and beta carbon, because that's going to be the orientation in regards to that carboxylic acid, or which is going to be attached to the coenzyme A, in regards to the orientation of where the cleavage is going to be happening in the thiolysis. We're going to have to know the 4 steps of beta oxidation. We're going to have to understand the transportation of fatty acids and how we break those down, particularly, again, the phospholipases, how we're going to target those individual triacylglycerols or diacylglycerols in regards to breaking them down, but also utilizing the role of glycerol in regards to triacylglycerol metabolism. Again, we're getting energy from that glycerol by converting it into via glycerol 3,1-phosphate and glycerol 3-phosphate and making dehydroxyacetone phosphate. So again, we should understand that. We also think about the hormonal component in regards to triacylglycerol breakdown. So that fat lipid component is basically present. We're going to present it with a hormone-dependent lipase, which is going to be dependent on phosphorylation from the protein kinase A, which is dependent on the adenyl cyclase system, which is then reliant on the GCPR system. We're going to think about the activation, importantly, of the esterification step, the priming step, in regards to activating fatty acids as a form of that carboxylic acid being a coenzyme component. Without that priming step, we are not going to metabolize our fatty acids. We're not going to be able to metabolize those fatty acids because without that coenzyme component, which is a leaving group, we're not going to get them into the transport system to move them through the double membrane of the mitochondria. Once we have that mitochondrial movement, we can then go through beta oxidation. We're going to understand saturated, monounsaturated, and polysaturated fatty acids, as well as fatty acids of an odd number. And noting the relationship, again, that propionyl-CoA feeding the production of succinyl-CoA, which will feed then the TCA cycle. So there's a lot to think about in this particular lecture. And I think you need to be able to master a lot of these things as they do pop up on the exam. I love putting questions in regards to, as I said, we have a radio-labeled monounsaturated or polyunsaturated fatty acid. Show me where the radio-labeled acetyl-CoA comes off. How many cycles of beta oxidation do you have to do? Where is the position of the fatty acid, or where is the position of the radio-labeled carbon in the form of acetyl-CoA? So they do pop up on the exam because it really demonstrates to me that you fully understand how to manage those fatty acids, the degradational process, where the carbon tracing is going in consideration in regards to rearrangement of bonds, if you need to, if they have double bonds, in regards to being unsaturated, and even if they're odd number fatty acids. So with that, we will leave it until tomorrow. I will actually post some lecture notes tonight for the continuing lecture. I wanted to finish this one because this lecture is really important, guys. You need to really go through this with a fine-tooth comb. The guys, Nick and Eric, will go again through this and emphasize aspects within the tutorial, the recitation, and you'll get some of this in the homework verbatim in regards to mastering the beta oxidational process in allowing us to access those carbon constituents, those 2 carbon constituents in the form of acetyl-CoA to feed the TCA cycle and to feed the oxidation and respiratory chain, as we'll see later on. Okay, so I believe I've finished. So yes, and I will talk to you guys tomorrow. So I'll open it to office hours and questions. So have a good day.